Welcome to the workshop. I've got Jackson with me for this video. He's going to help me do an excellent job. He's got his work clothes on. We are ready to work. Right? Yay! Okay, let's keep working. For a function f with domain real numbers, so x is a real number. So if we have some function and we took the limit of it, the limit as x goes to infinity of f of x. If this function actually has a limit, say L, then if we restricted the domain to the natural numbers, 1, 2, 3, 4, and so on, then the limit as n goes to infinity of f of n would be the same thing. What this tells us is that if we're trying to find the limit of some sequence, and we can write those sequences as a function of n, which has a well-defined function in terms of the real numbers, then we would be able to simply use the limit of the real numbers to help us evaluate the limit of the sequence. So let's take a look at that in an example. So let's show that the sequence with the given nth term converges. So in this case, we'll be looking at the function f of x equals the cosine of 1 over x, which is perfectly fine. Okay, of course, we can't divide by 0, so we can't plug in 0, but otherwise, that's fine. Right? If we're looking at the natural numbers, then 0 is not used anyway. So we know that they're equal at every natural number value. Okay, so the limit as x goes to infinity of the cosine of 1 over x is kind of difficult to think about. It'd be much easier if it were the cosine of just x. So let's do a substitution. If we let 1 over x be equal to t, then as x goes to infinity, t would actually go to 0 from the positive side. So we can rewrite this limit as a much easier limit to evaluate. So this is equal to the limit as t goes to 0 from the positive side of the cosine of t. But that's super easy, right? The cosine of 0 is well defined, and that's simply equal to 1. So we can say that the limit, hence the limit as n goes to infinity of the cosine of 1 over n is equal to 1. And we were able to use our knowledge of limits of real functions to help us evaluate the limit of a sequence. So whenever they match, whenever we have a well-defined function, then they'll match and everything is good. So last thing I want to mention for this video is the properties of limits of sequences. So if I were to take a constant multiple times a sequence and take the limit of that, then I can pull that constant multiple out. That is, the limit of a constant multiple times a sequence is a constant multiple times the limit of the sequence. If I wanted to find the limit of a sum of sequences, that's equal to the sum of the limit. And if I wanted to find the limit of a product of sequences, that is equal to the product of the limits. And finally, if I wanted to take the limit of the quotient of sequences, when I say I'm combining sequences here, I mean I'm just combining the nth term, a sub 1 divided by b sub 1, or a sub 1 times b sub 1, a sub 2 times b sub 2, a sub 3 times b sub 3, and so on. So the limit of a quotient, well, of course, we want the denominator to never be 0. So as long as the denominator is never 0 and both of the limits exist, then the limit of the quotient is the quotient of the limits. But that's all that I got for this portion of the video with Jackson. We will continue on with some more information about sequences in just a little bit here in the workshop. Right, Jackson? Plenty of work to be done. Let's see what we can do. Say hello, everyone. Hello, everyone. We're so happy. We can see Mama outside, which is great. That's why he's smiling. Oh, I mean, he's excited to see you guys, of course. We'll see you guys later.